Ok.
Foi? Foi. Bom, são 6 horas. Boa noite, então, pessoal. Meu nome é Felipe Dib. Eu sou o atual presidente da PGFRJ. Estamos aqui no nosso segundo dia de aula do minicurso do Douglas. Ele vai falar novamente um pouco sobre o Novva software, né? Para quem não assistiu a gente na última transmissão, na semana passada, o Douglas ele é formado na Universidade de Stanford. Ele é geoquímico com pós-graduação, no caso. Ele é o presidente da empresa Sirius Exploration Geochemistry e é o responsável por presidir a empresa e por ter por criar o software Novva, né, que é um software, sobretudo, de geoquímica, que ajudou bastante a gente no IBA, no início do ano, a nos consagrarmos como campeões mundiais, né? Como já é sabido. Aproveitando para informar para todo mundo que o nosso primeiro podcast, o primeiro podcast da FRJ Sedimentae, já está disponível no Spotify. O primeiro episódio a gente, inclusive, fala sobre o IBA, então, se você tiver mais interesse em saber como é que foi essa jornada para a gente, é só acessar o nosso link nas nossas redes sociais. E sem mais delongas, eu vou passar agora a palavra para o Douglas para que ele comece o curso. So, Douglas, I just introduced you in Portuguese. Thank you for your patience. And now you can start the second lesson on our mini course. Thank you.
Okay, can everybody see this? Boa noite. Thank you for the invitation to do this short series of lectures, and thank you for returning for a second evening of fun with basin modeling, or better, fun with integrated geohistory analysis. Last week I stopped at this point, and I'm going to continue in just a moment. But before I go on, I just want to remind you that in these lectures, I'm attempting to give you exposure to a lot of ideas about what IGA is and how you might use it. It's not comprehensive. There will be many topics that could fall in IGA that I've never worked with, and certainly I'm not talking about last week or this week. You're only limited by your creativity, but I wanted to give you a lot of ideas about how it might be used rather than showing you exact specifications for how you would do it. One of the things about basin modeling in general is there's always the complaint that you don't have enough data to build a good model. And if you have enough data to build a good model, you don't need a good model because you already know the answers. There is truth in that. But in IGA, the situation is somewhat different because our objective is to increase our knowledge and understanding in a comprehensive way in which we build linkages among pieces that are not necessarily normally connected and maybe aren't connected at all in this project. It's easy to use IGA to make progress. That is, because IGA doesn't focus on quantitative answers such as billions of barrels or whether you're going to find oil or gas, but rather focuses on learning about the geologic history and putting the pieces together better than they've ever been put together before. We can make progress even in areas with very little data. In other words, we change our objectives so that our objective is no longer a perfect model with very exact numerical answers about reserves or exploration risk, but rather simply an increase in our understanding. We walk away knowing more than when we started. This is a real life example. This is from Eastern Indonesia. You've probably never heard of this. The bird's head down here in the lower right is the northwest corner of the island of New Guinea. It's called the bird's head because it looks like a turkey's head. Far to the west here, we see the island of Sulawesi, one of the bigger islands in the Indonesian archipelago. And between them, we see the island of Halmahera. And right to the east of it, we see a little bay called Wida Bay. Well, Wida Bay is a geologic basin. And I was asked if I could provide a model of Wida Bay. I said, I know nothing about it. Do you have any information? They said yes, and they gave me a couple of papers and a couple of charts. And with that, in the space of about 5 hours, I put together a little model. It shows how you can do something with very little, and you actually can get some benefit from it. So the first slide emphasizes the tectonic complexity. Actually, this slide also does, because you could see all the sub-aquatic ridges and structures, and you can also see complex structures and mountain chains in the land today. But this looks a little bit at some of the faults and the subduction zones and so on. It's a very tectonically complex area. And you said you only have 2 papers and a couple of charts, and you have to make a story out of this. Well, I don't have to tell the whole story. I want to be able to say something new, interesting, and valuable as a result of spending a little time. So in the course of 4 or 5 hours, I put together a little story on the Wida Bay Basin. Here is a Novva model, a geohistory model of the basin center in the Wida Bay Basin. And what I've put down here on the overlays is tectonic events that I had identified from the papers I'd been reading. You can see it's been continuously tectonically active for its entire life, which is basically the entire Cenozoic.
Nice.
So very difficult, very complex.
Douglas,
But
can you hear me?
Hello?
Hello, it's Felipe. I'm so sorry to interrupt you, but we're not seeing your full screen, your presentation. We're seeing actually the slide 88. I don't know.
I don't know what to do about that because I am seeing the full screen.
Can you press ask and then try to
Yeah. Okay, so this is what you're seeing.
Yeah,
and there I'll just go to full screen. What do you see now?
We're actually locked on the Wida Bay Basin Center. Can you try to go forward and backwards on the slides to see if we see any change?
Are you seeing the changes? I'm moving around.
The slide is frozen.
Well, I don't know what to do about that.
So
it says I'm sharing another application window. I'll try that. Oh,
okay. Josias is telling us to put the slideshow on read mode, I guess. It's something that you did last week, if I'm not mistaken.
I don't know what I did.
Josias, can you give us a
Douglas, I'm here. Let me get my camera. So can you share your screen just like the same way you did some minutes ago? Just share your screen normally.
Select a window. Okay. PowerPoint slideshow.
Yes. Angela, assim que ele tiver com a tela pronta aí, você bota de novo, por favor. Okay, now we can see on full screen perfectly. Try to pass the slide and go back just so we can see if everything's okay. Okay, now it's perfect.
There you go. Now it's perfect.
Okay, great. Thank
I'm sorry,
you.
you can go on now.
Sorry to interrupt you
Okay.
again, Douglas. We can go
No problem.
forward now.
Okay, so I can continue now?
Yes, please.
Okay. Well, anyway, I put together a little story about this basin, and I want to share one little part of this with you just to show, number one, that we can do things even with very little information that help us in the sense of giving us new information we didn't have before. So we have to adjust our expectations to fit the information that we have. In this case, I had information that this time period was a deep water period. In other words, you see over here, the water depth is upper bathyal. Okay, so we're in a water depth a bit more than 500 meters. And then we go to very shallow water depth, shown here. I had that as information. So I adjusted my model to give me deep water, upper bathyal water at this time, and interneritic water at this time, much shallower. Okay, so that's an increase in our knowledge in that we now have this in a geohistory context. And what we see is that in order to get the water to be shallower, I have to have tectonic uplift in this model. So I've created a model where I went from a subsiding system into tectonic uplift that caused the water depth to shallow. And I thought, oh, that's interesting, that's nice, and so on. But a couple of weeks later, when I was thinking about this, I realized that I'd made a big mistake. It's the kind of mistake I warn people about every time I talk about IGA. And that is, don't create miracles. By that, I mean, don't find a simple solution that solves your geologic problems, but is very, very unlikely to happen. In this case, what we see is we had deep water, and then we uplifted to give us shallow water so that it fit the bathymetry information we had during the Middle Miocene. That is a miracle because it's saying nature knew that I needed shallow water, so it gave me exactly the right amount of uplift to give me shallow water. If it gives me less uplift, I don't have shallow water. If it gives me more, I have exposure on land. So this scenario is not likely. And so it really is not a good solution to the problem, even though on paper it may look good. So I went back and, oh, now I can't go forward. There we go. Okay. And I changed the model so that it's no longer a miracle. What did I do? And this is a very important principle to take away. The general idea that if you find a miracle in your reconstruction, you have to change it to get rid of that miracle. Instead of saying I had exactly 700 meters of uplift, plus or minus 50, I said I don't know exactly how much uplift I had. I'm going to make it a lot of uplift so that this didn't stop at interneritic depths. It went all the way to the surface and gave me dry land, which is a much more likely scenario than getting exactly 700 meters of uplift. This could be 1,000 meters, it could be 1,500 meters, it could be 3,000 meters. It gives me a lot of possible scenarios. So how do I get to shallow water? It's easy. It's erosion with a tiny bit of subsidence, perhaps. So what we see is a model that looks very similar. It's got tectonic uplift, but it's actually got more tectonic uplift. It's got an unconformity here during the uplift that we didn't have in the other model. We go back to the old model, there's no unconformity here. So I'm creating a new geologic history, and I start my sedimentation later than I did in my original model. But I like this model better because I think it is much more likely that this is what happened. So the progress in IGA depends on what you're starting with and what you learn. For me, this was a very successful exercise because I think I learned something new, and it reminded me to be more careful in my modeling reconstructions. I'm going to shift gears here and go to a topic that isn't really directly part of IGA, but it is strongly related, and that is geothermics. Many times our geologic reconstructions, things like paleobathymetry, tectonics such as rifting or formation of foreland basins, strike slip faulting, etc., may always, or all of them could have a relation to geothermics. And so you have to be ready to include geothermics in your thinking. So I want to spend just a few minutes here on this subject, which is actually not as difficult as you might think, and it's very interesting. The key bit of information in geothermics is Fourier's law, which is shown here. In its steady state form, it's very simple. The change in temperature over some distance, here it's usually vertical distance in real applications, but it doesn't have to be, is equal to the heat flow Q divided by the thermal conductivity lambda. Delta T over delta Z is what we call the geothermal gradient. So the geothermal gradient equals heat flow divided by conductivity. That's not difficult. And if you're going to be involved in any kind of basin modeling or really anything to do with geothermics, you have to understand this very basic law. But actually, Fourier's law is much more powerful than just calculating geothermal gradients, because you can rearrange it to give an expression for the heat flow Q. And then we can break that heat flow down into its component parts. So here we had total heat flow, and now we're saying that there's a lot of different possible contributors to the heat flow. And so this new expression is still equal to the same old term here, the conductivity times the geothermal gradient. What are each of these components? We have basal heat flow coming out of the very deep earth, out of the asthenosphere and also the lithosphere. We have the radiogenic heat production from radioactive decay in sediments, not just in basement, which is taken care of here, but in sediments here. We have, and that's always a positive number because we're always adding it. We can't subtract it. And then we have heat capacity heat that is stored in the sediments or released from the sediments, so it can be either positive or negative. And that is heat that causes rocks and fluids to become hotter when you add heat, or to become cooler when you take away heat. We also have two kinds of heating related to fluid flow. Groundwater flow can either be positive or negative, depending on whether it's hot water or cold water. And that is added to the flow of heat from the deep earth. And then we have hydrothermal flow, which is always positive because hydrothermal, by its name, is always hot water and therefore positive. So you see now we can take this very complex issue and break it down into manageable pieces that we can easily understand and work with quantitatively. And geothermics then can become a valuable part of your IGA work. They should always be there in your mind as a possible phenomenon that you may want to add to your discussion. And you can even rearrange this further if you wanted to calculate the change in temperature over a certain thickness of rock. We are interested in delta T, the change in temperature from the bottom of the rock to the top. And so we now have an expression for that. So Fourier's law is extremely powerful and valuable, and it is something you definitely should feel comfortable using. Okay, that's the hard physics for the course, and the rest is going to be more fun and more descriptive. I want to start here with a case from the Gulf of Mexico. This is a eustatic geohistory plot with the tectonic subsidence. Tectonic subsidence is the red line, and you can see from the non-flat sea surface that this is a eustatic sea level, eustatic geohistory plot because sea level is variable. It's got overlays on here that help us understand the history and clarify our thinking. So this is used both to help you and to help your communication with your audience. But what I wanted to show you here, in addition to all of that, we've got a lot of normal sediments here, but we've got the blue layer, which has the name salt. And what we see is it was deposited in the Bajocian here, 169 million years ago, and it was deposited and remained a constant thickness for a long time. And then it got thicker, a lot thicker. And then very recently, it got a lot thinner. So in this reconstruction, we have very active salt in our autochthonous salt layer down at the bottom. And of course, if you're working in Brazil, salt is something you would be thinking about in many of your basins. But we have another bit of salt up here, this magenta color I call D-salt for diapiric salt. This is salt that is what we call allochthonous. It has moved. It was not deposited here. It entered here either as an intrusive or, in my opinion, more likely an extrusive body on the sea floor with some dissolution, but a large, thick, salty section preserved to today. This is the kind of thing that we can work on very well with IGA, because IGA is interested very much in the relationship between salt thickness and changes in salt thickness, formation of diapirs, evacuation, and the sedimentation rates, because the structures created at the seafloor, either by salt evacuation or salt diapirism, will control to a significant degree depositional patterns of sediments because they disturb the relatively flat sedimentary surface you would get in the absence of salt tectonics. And one of the things that we have to be able to do with our software, and it's easy to do with Novva in building models that are as complicated as you want, but we see here the thickness of the autochthonous salt layer is shown through time in red. We had Bajosian deposition, followed by a long period with nothing happening, followed by thickening during the Paleogene, and then within the Neogene, we see that stopping. And very recently, in the last few million years, we see salt evacuation occurring at this location. Simultaneous with that recent salt evacuation, we have diapiric salt appearing near the surface. Was it the same salt that was evacuated here? Maybe, maybe not. That's not so important for us. But what we see is that simultaneously, we are taking salt out of the lower layer and we are putting salt into a higher layer. And that will, of course, affect geometries and sedimentation patterns. It may induce erosion. It may do all kinds of things. And in addition, it may be very important for hydrocarbon migration, formation of traps, sealing, and so on. So being able to build this in and make it part of your geologic narrative is extremely important. And the reason I put salt here right after geothermics is very simple. Whenever we talk about salt, one of the first things people say is high conductivity, so high heat flow, and then they say wrongly, high temperature. What we actually see is in this model, I think it's the same one, this is our temperature profile at present day, 0 million years. And what we see on this is it's not a straight line. It's not even a simple curve like a parabola. Instead, it has stages. Here it has a high geothermal gradient. Here it has a low geothermal gradient. Here it's high again, then it gets lower. Why is this? Again, it's that question why that we love to ask. Why? The answer is the areas with low geothermal gradients are the areas with salt because it has high conductivity. So we see our nonlinear gradient is a function of lithologic changes. Okay, that's good. We understand that. But we could look at it in more detail if we really want to. Here we've plotted heat flow as a function of depth. Again, this is present day. And this is thermal conductivity of the different rock layers. You'll notice the two salt layers have high conductivities compared to these. And that's what's responsible for the changes in geothermal gradient. But we also see that the heat flow is highly variable here. And that is because we're seeing a lot of other geologic events. One of them is radiogenic heat production, which I will talk about in another slide. But I want to show you all the things that might be related to having this irregular pattern of heat flow as a function of depth. But before I go on with that, I want to show you something that is extremely important for your narratives and for communication. You must pay attention to scale. In this case, this was the auto scale, and it shows maximum scale for the variation in heat flow. But you'll notice this down here is only 50.8 milliwatts, and up here the maximum value is 52.2. So there's hardly any real variation in heat flow here. In fact, if we plot it on a normal scale that goes from 0 to 60, we see there's very little variation. It's not perfectly even, but these events that we saw, they're not changing the story very much. And that is an important thing that you can add to the story by doing this kind of analysis. Again, we see the thermal conductivities plotted on their own scale, and they do emphasize the huge difference in conductivities between the carbonates and shales down here and the salts. But it also emphasizes the very low conductivities of these recent sediments, which are again a mixture of limestones and shales and sands. Very low conductivity, and we need to understand why this conductivity is so low. The answer is in part here. Very high heat capacities of this shallow layer. That means when you try to heat this up as you bury it, it takes a lot of heat out of the system. And do you know what component is responsible for most of the heat lost due to heat capacity? Water, which has a very high heat capacity compared to any rock minerals. And so these are very high porosity, shallow sediments with very high heat capacities and very low conductivities, whereas everything else has a much more normal heat capacity because of much lower porosity. We also can look at the radiogenic heat production. Our salts contribute almost nothing. Our limestones are limited. Our shales and sands produce more. Here, we aren't very productive because the water doesn't contain much radiogenic material. So the fact that we've got high porosity here hurts our radiogenic heat production. And with some practice, you can put all this together so that you understand all the components of the system, and that's hugely important in understanding and even predicting how it's going to behave. The last aspect of geothermics I want to talk about here is basal heat flow. And in this case, we have a double rift in the Gulf of Mexico. There was a failed Triassic rift, and in the Jurassic, there was another rift that gave us oceanic crust, but it didn't give us a full Atlantic type ocean. So you can call it a failure or you can call it almost successful, but it was a very serious rift. And one thing we can do is create a model for heat flow as a function of time, taking into consideration these rifting events. This particular model has two rifts, and it's based on my model published 20 years ago for rifting heat flow, which is an update of the Mackenzie model. But there are other options. I just want to show you, you can work out histories of basal heat flow that relate to your tectonics. So with that, I want to go into a couple of very interesting narratives to give you an idea of a little more about a more complete narrative than just one that takes one or two slides. In this case, this is something I did recently, just a few years ago, and it wound up being a total surprise because we were asked to do a conventional basin modeling study with maturity and migration and trapping. And it actually turned into IGA because we found so many things in the geologic concepts there that were just wrong, wrongly interpreted, overlooked, not put together correctly. And so I think our biggest contribution was showing them that the history is quite different than they imagined, and that difference gives us some new exploration plays. So we're turning a routine study into something different that is not academic, it is actually exploration oriented. And this is what you're going to want to do with your work, especially for IBA. You want to turn your good science into something that helps you develop prospects within the play, do some risk analysis, do some decision making. So you are after something very practical, and it is a very realistic goal. For those of you who don't know, Belize is located here on the east side of the Yucatan Peninsula. Here's the Gulf of Mexico. Here's the country of Mexico, Guatemala, Honduras, and so on. Here's Cuba. And what you can see is it is very close to the Gulf of Mexico, but it wasn't part of the Gulf of Mexico. So you can expect the possibility of some influence in the rifting of Gulf of Mexico that might have come down all the way to Belize. You'll also notice down here that this is the Corozal Basin in Belize, which is what we'll be talking about. It's very close to this transform fault zone here and strike slip faults through here, as well as the rifting in the Gulf of Mexico over here. It's been very close to a lot of very significant tectonic activity. That's our background. I want to show you, here's the Corozal Basin, our target. Right south of it are the Maya Mountains, which are latest Paleozoic in age with some possible rejuvenation. Over here on the boundary between Mexico and Guatemala, we have the North Petén Basin. South Petén is down here, but I won't talk about it. I want to focus on this part here to tell the story. The key component in this is the Red Bank Formation, named after Red Bank Village in Belize. And this is a well in Belize. And I have drawn it here with a standard geohistory plot. That means flat paleo sea level. That's our datum. It's always 0. In this, what we see here is this became dry land early in the Cenozoic and is now about 250 meters, maybe a little more, above sea level. Okay? In this picture, the only way to get this above sea level is tectonic uplift. So we see our tectonic subsidence curve going up, which means tectonic uplift. Okay, that's interesting. Most people would stop there, but I actually built a eustatic geohistory plot, And what we see here is the sea level is going up and down. It reaches a maximum here at about 53 million years in the early Eocene, the Precene. And what you see here is this drop in sea level has exposed this area, this location, for 45 million years. It's been dry land, not because of tectonic uplift. We don't have to put tectonic uplift into our model. It's actually a period of tectonic subsidence. But what happened was the land didn't go up above the water fell down below the land. That makes a huge difference in your tectonic concepts, and it turns out to be the key recognition that gives us our new exploration play idea. The Red Bank Formation is this one, the yellow one here, Neogene in age. It is a non-marine clay in a basin where everything else, except a very few local sandstones, is either limestone, dolomite, or gypsum. Gypsum anhydrite, better said, anhydrite. So we have limestone, dolomite, anhydrite, and we've got a little bit of clay in one small area. Why do we have that clay? There's that question, why again? Why do we have that clay? Well, non-marine clay, that suggests that it came from land. Where's the nearest source of sediment? Well, the only thing I mentioned to you was the Maya Mountains, which it turns out are very close to where the Red Bank Formation sits. It's very local in its distribution. This non-marine clay infills a karst sinkhole. There's a lot of karstification here, as you can imagine, because this has been exposed. All these carbonates exposed here for 45 million years. And so now we're beginning to develop a depositional model. Believe it or not, nobody had ever thought of this. And it was us basin modelers who discovered it. And so we have a new mechanism for creating accommodation space. And we now have a suggestion of a source for our clastic sediments. And we can put all this together if we're smart and get some new exploration ideas. Another key is that this Cenozoic karstification and infilling, very recent Neogene, occurred only in a limited area, and that limited area is precisely where the two small oil fields in Belize are located. Is this a coincidence? I don't believe much in coincidence. I think when you see a coincidence, you should start looking for a better explanation, which means cause and effect in some relationship. So I started thinking about this. Is it possible that the karstification somehow played a role in the accumulation of oil precisely in the area where this karstification was? Here we see the Red Bank Formation, age middle to late Miocene, very localized here in its known and proposed distribution in the southwest corner of the Corozal Basin. No Red Bank anywhere else. The Maya Mountains are right down here, so I think it's unquestionable that this is the source. So now we have to imagine sedimentation, transport, and deposition patterns leading out into the ocean. It seems very logical that they would do something like this. And then it turns out that the two oil fields in Belize are not at all in the red bank or anything young. They're in the hillbank sandstones, a thin layer, couple of thin layers that are 200 million years old. They're latest Triassic in age. So 200 million years of time difference between the hillbank and the red bank. But I believe they both are controlled by the same factor. I believe that 200 million years ago, we had erosion at the foot of the Maya Mountains. Here are the Maya Mountains. At the foot of the mountains, we developed transport patterns, rivers taking the sediment toward the old sea, and that this led to karstification of the hillbank limestones. And the Maya Mountains provided a coarse clastic source, and the preferred pathway was following the water. So right here, 200 million years ago, we deposited the sandstone. The only sandstones known in the basin are within the hillbank formation, right in the same area where we're finding the red bank. So I look at it as rejuvenation, that 200 million years, 190 million years later, the same process is operative. It gives us red bank. It doesn't give us oil. It doesn't give us a reservoir, but it gives us an important clue to understanding the entire petroleum system in the upper hillbank. And when you understand the petroleum system, then you can start saying, where else could I use this knowledge? So let's review what we've got. Drainage of water and clastic from the Maya Mountains since about 200 million years. Deposition of limestones and dolomites in marine environments across the Corozal Basin. Karstification through time, possibly in many layers, in these long-lasting or at least intermittently present flow pathways for water and sediments. They may have been rejuvenated periodically by tectonic movements of the Maya Mountains that would have kept the juncture between the Maya Mountains and the sediments of the basin cracked and permeable. So in red here, we see some questions for exploration. Are there other sandstones, perhaps in the Cretaceous and early Cenozoic strata in Belize? In other words, is it just the late Triassic, or could we find it in younger ones? What implications does the understanding of karstification have for understanding carbonate reservoir and seal facies? What about oil migrating in from the west in Guatemala? The source rocks are of poor quality and immature in Belize. The basin is not deep, so it almost has to come from Guatemala. So if we know it came from the west, what exploration opportunities do we have in eastern Guatemala? This is the exact geometry that an explorationist would be looking for. A mature kitchen where he strongly suspects or knows there is mature source rock capable of sourcing commercial accumulations. He has another area that has shows or discoveries, such as the small oil fields in Belize. This is over in the Petén Basin of Guatemala. So you don't have to be Einstein to realize this is where you should be prospecting. Between the source of the oil and where we know some oil moved to. Get in here, find a trap, find a seal, find a reservoir, and you're in business. But it gets even a little better than that. When we go to the North Petén Basin, the Shan oil field produces 90% of Guatemala's oil. It's just the Western version of what we're proposing here. This is where the oil fields are in Belize, in the Corozal Basin. This is only about 100 kilometers. It's not a long distance. It's not a difficult migration. We have plenty of maturity here. It can flow west, up dip in that direction. It can flow east, up dip here. So get a concession in here, maybe get a concession in here, maybe even go north, maybe even go into Mexico. There's all kinds of interesting possibilities that come out of this if you think like an explorationist instead of a basin modeler. I want to finish up here by quickly going through a rather long story that is in a YouTube video that I created that you can find on the Sirius Exploration Geochemistry channel. It's about the Münsterland 1 well, a science well drilled to 6,000 meters a little bit over 60 years ago in northwest Germany. It was extensively studied, great data set. It's been a favorite area for German students to build basin models in, particularly 1D models. And this is what you typically see published by them, a published 1D reconstruction. This is what we're starting with. I took a look at this and I said, I don't like that. I think there's some problems with this model. We've got very rapid downwarping here and accumulation of thick layer of sediments. Nothing wrong with that. We have very rapid inversion, building high mountains very quickly. In principle, nothing wrong with that, but it does take special conditions. Then we had the mountains crashing down quickly enough to give us a new basin where we could develop or deposit a very thick layer of rock that wasn't even in shallow water. So tremendous tectonic subsidence required for this to happen. And I said, boy, you're asking a lot of gymnastics of this, these rocks. I wonder if all this is really smart and necessary. So to explain this proposed geohistory curve, I've got the Variscan foreland in front of the Variscan thrusts in the Carboniferous, got Variscan uplift as the thrusting overrides this area. That gives us our mountains. And then we've got sagging here as Pangea falls apart. And then an uplift of unknown origin, possibly a pull-apart basin to give us the accommodation space to deposit our Cretaceous section, which is real because it's present today. So I said, okay, if I'm going to accept this model, this is kind of what I have to expect. And at this point, it's good to remind yourself every number that you put into your models has physical significance, and you must choose them carefully. If I say this rock is 50 meters or was 50 meters thick when it was deposited, that automatically implies some things about sedimentation rates. It may also imply things about lithology, transport, etc. So when you build your models, don't just throw in numbers and not think about them. You have to understand that they have meaning. So the real question is here. Here's the Münsterland Basin and the Münsterland 1 well here. To the north of it, we have the Lower Saxony Basin. To the south of it, we have the Rhenish Massif. The Rhenish Massif is a highland, whereas the Lower Saxony Basin became a Triassic graben as Pangaea fell apart. So the question is, which world does Münsterland belong to? The people who built those models clearly believed it was more like the Lower Saxony Basin because they have Lower Saxony subsidence and sediments and sedimentation there. But I want to explore that idea. So here in this block diagram, we see the Münsterland 1 well. The purple here are the Triassic and Jurassic age sediments. To the north here is our Lower Saxony Basin. Rhenish Massif is to the south. Rhenish Massif was never buried by sediments. So if we're in the Rhenish Massif model, we will have no Cretaceous or Jurassic. We'll have younger rocks, Cretaceous, sitting on old Paleozoic basement. But if we accept the Lower Saxony model, we're going to have all this deposited and then later eroded. We have to choose. The Münsterland is pretty close to this. It's not that far from this. And we're going to have to decide. The people who built the last model already decided, as I said, for the Lower Saxony model. My problem is the Lower Saxony Basin model requires huge Hercynian uplift, followed by extremely fast and complete Permian collapse. It's like baking a cake in the oven. If you bake it at the wrong temperature for the wrong time, it'll go way up, and when you pull it out and it cools, it all comes falling down. Very dramatic, but is it a good geologic model? Well, fortunately, we have the world's best set of vitrinite reflectance data available, but nothing from the Cretaceous. It was only for the Carboniferous. You say, why is it the world's greatest set of data? It's because this is the area where vitrinite reflectance was developed as a technique for coal maturity or coal rank. These were the scientists who had developed a vitrinite reflectance for that purpose, working on this more than 60 years ago. And obviously the data were very well behaved because they've got this incredibly beautiful vitrinite reflectance profile until we get down to super mature things with reflectance values of 4 to 6, and then it begins to deteriorate. But this is the best vitrinite reflectance profile I've ever seen. We can trust this if we can trust anything to do with vitrinite reflectance. That's going to be very valuable for us. And that is something that you will want to do in your IGA. Frequently use geochemical data or other kinds of data to test and calibrate your ideas. Okay. Now I'm going to leave this for a moment while we talk about tectonics. In creating a narrative, and I'm really big on creating narratives, and that's a major theme of today and this whole series of lectures, is we always work with analogies, even if we're not recognizing it, because we have experience and we're always drawing on that experience to help us with our new problems. The problem is some analogies are more appropriate than others for our problem. No analogy is perfect. And there are a lot of factors that can make it difficult to choose a good analogy. In my opinion, the Münsterland study suffers from 2 false analogies. The first one is imagining that the collision, the Hercynian orogeny, was like the Himalayan orogeny. The Himalayan orogeny is an anomaly. It is very unusual in being so strong and so perfect. You're not going to find orogenies where things meet in this geometry and with as little interference and complications as India. So don't think about India. But the temptation is very strong. Back in the Carboniferous, the Alleghenian orogeny, which is down here where the Appalachian Mountains were formed, they have very mature vitrinite there in their coals. They had a very serious collision with Northwest Africa, Morocco in particular. There, the analogy with India is probably valid. But Münsterland is up here. And the problem is, this was a lot of little microcontinents that had been sutured together that were not colliding head to head. It was more side to side. So these were weak collisions that were probably, in my opinion, not capable of building such high mountains. And this makes the same point. The Alleghenian orogeny down here in Laurussia or Laurentia is a rather long way from the Münsterland location. And here's our Hercynian Variscan orogeny. It's nowhere near as strong as this one, certainly not as strong as the Himalayan, and it is more the model that we're looking for here. So that brings us to the question when we say, well, maybe we need to rethink our collisional model, and the analogy for that is, what do we really know about this? We very quickly can confuse our ideas, our beliefs, our wishes with facts. So we have to keep reminding ourselves what is really true. In this case, what do we really know? We know we've got two unconformities, one on top of the Campanian and one on the top of the Carboniferous. Okay? We don't know anything about the Lower Saxony Basin or the Hercynian from just looking at the rocks today, unless we can get data like vitrinite reflectance out of these rocks that helps us understand. So keep bringing yourself back to reality when you're doing your work. Don't go off into dream worlds about things that can't be true. And so here's our original model with a red line for tectonic subsidence curve on it. And you could see we are asking these poor rocks to do a lot of crazy things, a lot of ups and downs here. I don't like those mountains being that high, so I can lower the maximum elevation. I don't need 6-kilometer mountains. I can do what I need to do with 1.5-kilometer mountains here. I can still deposit and erode the same material. I just need to look at erosion differently. In the original model, they moved the mountains up very fast and then started the erosion. So most of the erosion was post-orogenic. In my model, I would start the uplift a bit earlier and I would make it slower and I'd make the erosion faster so that my mountains never got very tall. And that means I don't have to have so much tectonic subsidence at the end, because instead of 4-kilometer mountains, I have 1.5-kilometer mountains. So that might be compatible with the Lower Saxony Basin model. We might be able to send that down enough to make it work. It's going to be easier in any case. And if I really make it an extreme case, lower the maximum paleo elevation to 500 meters, it becomes quite easy, okay, to do this. But I don't really have mountains anymore. Am I happy with that? Why might you want lower maximum paleo elevation? It requires less tectonic uplift and more syntectonic erosion. That's fine. You can have overlapping events where mountains are going up and the surface is being cut away at the same time. So I think the second false analogy here is taking the Lower Saxony Basin as your model for the history of Münsterland. I don't like it because of the difficulties with the geometries, the tectonics, and so on, but also it isn't super close to the Lower Saxony Basin. To me, it fits better into the Rhenish Massif province for my taste. So here we go back to our original model just to show you again. And now I look at our version here. It's looking pretty calm. What has happened since the last one? We got rid of the Triassic. We said, let's try it without the Triassic. Let's move to a Rhenish Massif model for this area rather than a Lower Saxony Basin model. And this looks pretty good. We've got a good downwarping here for a major collisional event. We've got a weak uplift. And then after that, it's really pretty quiet. We do have a new event here we would have to worry about in the Cretaceous, but we have that regardless because we have to explain why we were able to deposit such a thick Cretaceous section here. One of the interesting things was they had beautiful temperature data, and after modern corrections, I wind up with this nice temperature profile, which gives me a nice sense about paleo heat or heat flow today in the basin. This is my line fitting these data. And then using a constant basal heat flow through time, the one that fit this, 58 milliwatts, I used it through time just to see how it worked. And I see that up at the top of the Carboniferous, it gives me a really nice fit to the vitrinite reflectance, but it isn't a good fit deeper in the section because these rocks have clearly been hotter than my model, which is these rocks. We need to rotate this line back to go through these data points. And the reason for rotating is that is what happens if we raise the heat flow. The line is more strongly affected by this down at the bottom than at the top. In other words, a change of temperature of 20 degrees matters a lot more at a high temperature than a lower temperature. So I would say I've got the right amount of erosion put into my model here. I think it was about 1,900 meters, which is geologically not unreasonable, especially if it's got 100 million years or 150 million years of time to erode. And so we're starting at a good point here, but we need a higher heat flow. And I was saying, well, what could be the source of that heat? And I found a paper. It was amazing luck that talked about volcanism in this area. Here you see the orange and the red are volcanic rocks with or without sedimentary cover. Here's the Münsterland well. Wow, here's the Lower Saxony Basin right up here. So the Lower Saxony Basin was a rift basin, a Triassic rift basin. We know that from its sedimentation history. And this is volcanism, which has been dated to the latest Carboniferous early Permian. So it is volcanism occurring right before the rifting. That suggests to me that some of this heating, relatively minor heating, possibly rather temporary, could easily have affected the Münsterland area. It's only 100 kilometers here, and you're in volcanic rocks. So I took that as an indicator that my model was reasonable. And so I put in an event here very simple, where I've got this cooling lithosphere, and then I just put in some volcanism for, I don't know how much, I don't know how long. By trial and error, I just put it in at approximately the right time, which is in the late Carboniferous to Permian here. And voila, we have quite an amazing fit to this beautiful trend of vitrinite reflectance data using this simple model. So here we are back at the original Münsterland. Here we are at my most recent version, which looks quite different than that. And I feel like we've made a lot of progress by rethinking this model. So to summarize, geohistory plots have been available for a long time, but they haven't been routinely used by most groups, and they've rarely been used to maximum effect. As I've said before, most of the time, geohistory plots wind up as pictures on the cover of a report without any further discussion. Unfortunately, that's nice, but it hardly justifies creating them and working with them. What we need to do is to learn how to make maximum use of geohistory plots. Going further, the eustatic geohistory plots, and as far as I know, I'm the only person who's doing this, represent a unique and extremely powerful tool for geologic analysis. There's nothing like it. IGA should become a routine tool in every geoscientist toolbox. Appropriate software, like mine, designed for this purpose, could greatly facilitate IGA. And the best case is when your IGA is linked interactively with people involved in biostrat, sequence strat, normal seismic interpretations, and other geoscience disciplines, and their knowledge, their data, their opinions can serve as QCs from those technologies in the whole story. To summarize then, as Wallace Pratt famously said, and it's very often quoted and it's really true, oil is found in the minds of men, and had he been born later, he would have said, and women. And that's what we're trying to do with IGA. We're trying to use our minds as well as possible to aid in the exploration process. And if you're not interested in oil, you could still apply this mode of thinking, the creation of narratives, the interrogation of your data into any other discipline you want to apply it to. New ideas are essential if you want to have a future in exploration, as a person, as a scientist, as a company. And IGA is far and away the best available tool for generating new ideas. That's what I hope you can do in your IBA. So it's IGA and IBA as happy partners. I believe that the application of IGA as a thinking tool to build better models and create better narratives, create and present better narratives, is a huge step forward compared to using IGA, or I'm sorry, Bayesian modeling simply to create output for related to maturity or generation. It's much bigger and better than that. So I hope in this coming year, your IBA team can take, with IGA, can take Bayesian modeling and Novva to a whole new level of application that will be very rewarding and will amaze the judges. I think a concise statement that summarizes all of this thinking is the journey is the destination. if you're only interested in billion barrels of oil in your basin or your prospects, you're going to get to that answer as quickly as possible, and you're not going to learn very much. Enjoy the journey. Enjoy the model building process. It's really fun and interesting. Geoscientists should do more with time and with history. They should do much more with narratives. I think that's part of the reason many geoscientists entered geoscience, but in the current world, they don't get to do much of it. Have more fun with your work and take the Zen approach that the journey is the destination. What we're really trying to do is to have an enjoyable trip as we learn more than anybody else. So thank you for listening to a lot of that. I'd like to take a 5-minute break now, and then we'll come back and talk. I'll do a little bit of a demo with Novva, and we'll have some questions and answers if you would like at the end of that. So see you in 5 minutes.
Yeah, thank you in advance, Douglas. It's been great, and we can do a 5-minute break. No problems. So
Okay,
we go
very
back
good.
to 5, right?
Okay, I think our 5 minutes has passed, and so I'm going to get started again. I want to show you a little bit about Novva. The first thing about it is that it is for all geoscientists, not just specialists. The design is intended to help people, and even it allows people who don't use it very often to not forget how to use it. So what I'm going to do here is click on this opening screen, and it's going to give me an option. I can open an existing study, create a new study, or whatever I want to do. I'm going to open an existing study, and it's going to be from the Permian Basin, the Midland Basin part of the Permian Basin. It's a very small one. I've just got 4 or 5 models in it. And I'm going to open one of the models. You'll notice that the models, each one has a name, whatever name you want to give it, and it's a .nov file. That is the model for an individual location. It could be a well, it could be a pseudo well. Each of these, we have 5 different models in our study. So we've already opened our study. It's called midlandbasin.cmn. CMN stands for common. And that file is the master file for the study. It has information like lithologies and their properties that would be used by all the models. But then the individual models would have information that only belongs to that one location. So let's say our lucky number today is 12. So I'm going to open M12. And now I click on this button to enter the interview. And what we see now is we have 4 tabs up here: rocks, thermal, hydrocarbons, and output. And then under each of these, we have other tabs. And under each of those, we will have other tabs. So we have everything in a systematic way. And when you first build a model, you must start at the beginning and go through it completely. Later, like now, because we already have our model built, I can jump around into any area that has already been entered. But I'm going to start with just a few things here in the opening section. We can work with units. I can change feet or meters. I worked here in feet, but I've changed it to meters for you, Celsius and Fahrenheit. The well location, I chose here to use decimal degrees, but if I went to degrees, minutes, seconds, it's now telling me I can't use these decimals and I have to fill in minutes and seconds. My third opportunity is UTM. And if I want to do UTM, which is also called easting northing, I have to put in the zone and the easting and the northing numbers here. And then it will tell me what the latitude and longitude is. So I get my choice here on how I want to do this. I'm just going to go with what was already in here, which was decimal degrees. And you could see it's happy with all this. There's no red warnings, no blue boxes that require data. However, if I click on more info, and we have many more info buttons in the screens, we get additional information explaining things, discussing science, discussing names like easting and northing, because not everybody's familiar with all of this. So it's designed to help people. We have in our model here 2 different options for reconstructing paleolatitude. That's important because of climate and surface temperatures. One is from Chris Cotis, which is, well, it's been going for 40 years, let's just say. And the Earthbite group at the University of Sydney, maybe for 10 years. So this one was done using Chris Cotis, but I can change if I want. And what this shows, if I go here to more info, I get a little bit of info about Chris Cotis, but I also get references with hyperlinks. So if I click on Sabine Zahirovic here, I'm taken to that particular entry. And so I can then look that up if I need that for something I'm doing. So we have a comprehensive list of references. For example, if I go to tools, I have general references, and I also have a separate section with references for source rock kinetics only. There's also a geologic age chart, which is here. There's a number of different options. I haven't updated since 2016, but it's not too badly different. And it shows lots of these with tool tips, which we put in that show the ages in that system. Now I can go to another geologic time scale, and some of the ages may be a little different than they were in the original one. I'll just go back to the most recent one here, but you can pull this up just to get ages at any time just by reading the tooltip. We have to enter the present day elevation or water depth. Now this is onshore. It's in West Texas. So I click this button. If I clicked offshore, that's fine. It's asking me for water depth. It doesn't delete this information. I can come back to it. 683.36 meters at this location. Okay. This is a well with a known TD, so I enter that here. KB elevation, well, it wasn't very high, 10 feet, I guess, above ground level, and so on. Now, here's one of the interesting things. This is where you can create your own overlays if you want. Those overlays can appear in your output, but you can also not show them if you want. So let me just show you here what we did for this basin. This model, the original basin type, basin forming event, we said in the earliest days of our model, this was actually a broad shelf. You see, these are the types of basins we use. This is to stimulate thinking much more than anything else. So it's not necessarily comprehensive, but it allows you to think about the geologic history. Here is the name that will actually appear on the output. And we can enter this ourselves here and just paste it in or type it in. We also can have a start and an end time for each of these events. Now, right here, it shows for all the other wells in the study, we had 5 total. So this is all 5. We had the same story. Broad shelf, Tobosa Basin, passive margin, same ages. But they could be different. I could make this 400 here if I wanted to. And you'll see down here, it changes very much the appearance of this. So we present the same data in 2 ways, as numbers and names in a table and as graphical here. Under more info, you'll see a listing and explanation of all the different types of basins, basin forming events that we have, again with links. And once I'm done with that, maybe I'll just put this back to 500 here. We can add other tectonic events in the history. In this model, we've got a lot of events. We have adjacent folding that I have given the name pre-Ouachita wrenching. Ouachita is a major orogenic event in this part of the world. So this is before the real or Ouachita. It was when some outlying island arcs started interacting with the margins of the Laurentia terrain from which it was coming. We have wrenching, extension. We have loading-induced downwarping. We have sagging, more loading-induced downwarping. And then we've got some uplifts here. It's not continuous. It could be, but here we have our last uplift was only 5 million years ago. Before that, the end of our last event was 50 million years. So we have time gaps here when nothing important was happening tectonically. And this is what it looks like in time. Our basin forming event, then our wrenching, then our other events. Some are short, some are long, all the way up to present day. Let's see. Can't get that to move. Anyway, not important right now. When we're done with that, we move on. Oh, I guess I should go back and say, one of the nice things about this is I have all of these models open in the background. I'm working on this model, but all these other models have the same information in here. And I can edit all of my models from this screen for this. If I want to. It's just a convenience to make it easier to keep things consistent. I want to show you, I can't show you everything, but I just want to show you the stratigraphy here. This part is designed to be familiar and comfortable to a geologist. So it's designed like a strat column in which that's the entire thing that we've put in. We have unconformities, we have depositional events. All of these are rocks that are present today, because this is the present day stratigraphy. That's what the instructions say. Enter the present day stratigraphy the way you want to subdivide it, with all the names just the way you want them. Dewey Lake, Rustler, Salado, Tansel, Yates, Seven Rivers, Queen, and so on, all the way down. We've got unconformity above the Triassic. We've got an unconformity below the Triassic. So we've got two unconformities, but a lot of continuous deposition. As we get to the older section, we have more frequent unconformities. And so on our first screen, we put in what is there today, the names of our layers or the existence of an unconformity. And we have to put in some combination of tops and thicknesses that will tell us how thick every unit is. So for example, right here, all of these are tops because this well drilled all the way to the top of the Ellenberger, 2,639 meters. And we said 61 meters was the present day thickness of the Ellenberger. So we now have completely defined the present day stratigraphy. Okay. The next slide or screen under stratigraphy is the ages, the age at the bottom and the age at the top. So each of these is actually an event. Deposition of the Queen, deposition of the Seven Rivers, and something happening here during the unconformity. So we want to think of this as a period of time when deposition was happening, 281 million years to 268. No time gaps are permitted here. We must have continuous time. But we don't actually have continuous time shown here. 327 is the age at the top of the preserved Barnett. 311 is the age at the bottom of the overlying Atoka. So we are missing 16 million years of time. That is going to all be explained by this unconformity, but that comes in a later slide. Okay, we allow layers to deform or dissolve in the subsurface. If it's a salt, it can dissolve. If it is any other kind of layer, it can deform plastically, but it's mostly going to be used for salt or for shale, if you have shale diapirs. So that's an option. We didn't happen to use it, but if I wanted to use it, for example, for the Salado Formation, which is a salt, or Salado, there we are. I could just check on this, and then it's going to ask me for information about what happened to the Salado. When did it get thicker or thinner by salt movement? So I skip that screen. But I move on now to unconformities. We had a lot of unconformities here. And what I want to do is talk about, let's start with a simple one, the post-Mississippi lime. And what we have here is our reconstruction of the unconformity. When we first opened this, we only had what is present below the unconformity, Mississippi lime, what is present above it, the Barnett. The user filled in by creating these two lines. He said, we deposited some Mississippi lime and then we eroded it. How much did we deposit? 45.72 meters. Now, why that? Because that's a round number in feet. It's probably 150 feet or something like that. In fact, if I go here, change depth units to feet, yeah, we have 150 feet. So we deposited 150 feet of Mississippi lime during this period till the end of normal Mississippi lime time. Then we eroded it over the next 13 million years. So we deposit 150 and we erode minus 150, and we call it an erosional event, and the first one is depositional. Now, why did I choose these numbers? Well, the preserved Mississippi lime here is only 48 feet. And I decided for some reason that I needed about 200 feet total originally. So I deposited an extra 150 and then I eroded that same amount because this is not present today. This is present. I can't erode that. I can only erode this. So this and this have to be the same. One's positive and one's negative. And after the Mississippi lime unconformity is finished, I deposit 21 feet of Barnett on top of that to complete the unconformity. Where did these ages come from? Well, 355 to 345 was the total age for Mississippi lime. I divided it between this and this in the approximate ratio of 3 to 1. And that gave me similar sedimentation rates for the two. And that's a statement that the Mississippi lime that was eroded is probably just like the Mississippi lime that is preserved. That isn't always true, so you can work around that by creating more complex unconformities if you want. But here we have a complete unconformity, and we have it shown graphically here, where this is the rate of deposition of the preserved Mississippi lime. Then we go to the eroded Mississippi lime and deposit more, and it's almost a perfect straight line because the rates are almost identical. Then we erode that at a rate that I know because I decided end of Mississippi lime was 345, so that left me 13 million years to do my erosion. That yielded a slower erosion than deposition. Deposition here is 3 times as fast as the erosion. And you can kind of see that this slope is less than that slope. And then we deposited on top of all this our barnett. So this is a picture of what has happened in our unconformity. And if I make a mistake and do this, I get an error message telling me these don't fit. I get an error message here showing that I didn't deposit enough material to erode this much. So I could fix this by making this minus 100. Now it's legal, but my rates aren't the same anymore. So I have to find some solution here that will be a good compromise among rates and thicknesses, timing, concepts, and so on. This is pretty comfortable. You just have to do that for every unconformity. And I want to show you the post-Triassic because that's the complicated one. Triassic to present, that's a very long time. It's over 200 million years. So we have deposition here, and this was all reconstructed for me by a professional, person who really knew the stratigraphy. Here's my Triassic, preserved here, eroded here. I deposit Triassic, eroded, and then I start depositing all my Cretaceous and Paleogene, and then I erode it in 2 separate events. This is one tectonic event, and here's another stronger tectonic event that influenced it more because the erosion is faster here than it was here. And we can see that if we go up to the present day and look at the rates. Whoops. Well, this is the rate of erosion. Well, it doesn't really show the rate of erosion of all that because it's several different events. We had to deposit and erode every one of these individually. So I deposit my 79 extra feet of Triassic here, and that was the first one deposited, and it's going to be the last one eroded. Okay, but you see, we didn't just oh, sorry, this was the rate. We deposited 500 feet and then eroded 470 here and left a little bit of Triassic and then eroded it in the second unconformity. This is another basic principle. Don't let your erosion go down exactly to the bottom of a formation. That's not realistic. Erosion will either leave a little bit of the overlying formation or will go down into the underlying formation some distance. But it will almost never stop exactly at the top of a formation. It's just a little detail that will help you show that you're a good thinker and a good scientist. So I think I'm going to stop here. This is our 2 hours almost, although we got a slightly late start. There are many, many more things in Nova that you can discover for yourselves. I just wanted to give you the confidence that you can do it. You can run Nova. I want to build a plot. I'm going to do a burial history here. It says burial history, but I'm going to put in tectonic and total subsidence. I'm going to show the tectonic events, and I'm going to do a geohistory with Eustace. So I'm going to show a lot of stuff on this geohistory plot. It's taking a little bit longer because I think it's got some salt in it. But here we see our model. You could see sea level going up and down. Here, you could see the overlays that we put on. And if I want to, I can go to View, Plot Settings. I can go to Overlay. I can, oh no, I'm sorry, that's not overlays. Special features, tectonic events. I can uncheck any of these that I want. So for example, I could do this one, uncheck the Toboso Basin, it goes away. So I could show selected tectonic events on this. All these are color coded to the ICS official colors. What we see in this location is the only things we have really are the orange and the lilac here, meaning that only Permian is retained here, plus a little bit of Triassic. The Cretaceous was deposited and completely eroded after it was deposited. So this is what our output can look like. And the beauty of these is they're fun and interesting to try to understand, because the objective of building this is to learn so that your model can become better, but also so that you can create and present a better narrative. So that means you have to understand, why was accommodation space created for the Green Cretaceous? That's shown right here, the severe Foreland Basin. Foreland Basin in front of the severe orogenic front pushed the land surface down at this time and allowed a Cretaceous section to be deposited here. So it's part of our story. And we create the diagrams to tell the story we want after we use the diagrams to understand our narrative. And there are many other types of diagrams that you can make. In terms of licenses for Nova, everybody who is attending this who is not affiliated with the university can get a demo license for about a month by just contacting me by email, or go on the Sirius Exploration Geochemistry website and go to the right place and just send for info here saying you'd like a demo license. We're happy to provide a demo to all of you who aren't with the university, and I hope that your institution or whoever you're with would like it and maybe buy a copy or a license. The demos are fully functional, but they'll come up with an irritating wallpaper in the background. so that your output figures are functional but not nice looking. So that's how we fight piracy. But you can be in contact with me if you're interested in a demo. If you're with the university and you're in IBA, those IBA licenses should be long-term until the end of IBA, which is probably at least 6 months. But they're only for the IBA people. And they're individual licenses for each of you. Those will come when your advisor sends me a letter. So he should be doing that as part of the process of getting your IBA licenses. If you're with the university and not in the IBA but would like a demo, I'm going to give for a couple of months a demo license for multiple people to the university. And I think Josias will be, at least for the moment, in charge of sorting that out. We'll send the license to someone at the university. Then it will be available to all the people at the university for those couple of months. In the end, I would hope that you would purchase an academic license. It's a 99% discount from the regular price, but I have to charge something for the university, which can be used by all students and faculty for educational purposes, including work on thesis and classroom work. It's not very expensive. It's permanent, one-time charge, and I think it would be an excellent investment for your university. So that's the story on the licenses. If you've sent me an email requesting a demo, I'm not going to answer those because the program for the demos has changed a little bit. So I'd like you to contact Josias or whoever he appoints to be in charge of this. With that, I think I'll open this to questions on anything I've covered or even things I didn't cover if you think I could maybe help in some other area. So thank you for attending, and I appreciate the opportunity to connect with your university and hope to continue the relationship in the future. And I wish you all luck. Those of you in IBA, doing it 2 years in a row would be astonishing and really great. But just the experience, especially using IGA principles, should be a wonderful learning experience for you. Those of you not in IGA, I hope you enjoy your demo experience and that you will get a chance to do work with Novva later. So thank you very much.
So thank you, Douglas, for the explanation. It was great. I think everyone could get around Novva software, at least the basics, the 101. I think the main scope of the software, it was pretty clear and everyone understand. So thank you once again for accepting our invite and explaining it to everyone, not just the Novva software, but the geochemistry in general, of the study cases, of the basis that you provided. So I have a question for you in terms of result quality of the geochemistry modeling. How much time would you say would be appropriate to dedicate on basing research and data filtering, and how long would be appropriate to perform tests within the software? Because during the presentation you said that it is very important to be aware of the data that is used as input in the modeling. But how should the workflow be in a little to unknown basin, as it usually is in the case of the competition, the IBA, where we just get to know the basin in a pretty quick environment.
Well, every study is different. I've done studies with 1 or 2 models. I've done studies with as many as 170 models. Somewhere in between is good. 20, 30 models is really nice because you get a lot of data and you can investigate many different parts of an area because not all of them are geologically the same. How long does it take? It depends on the size and how much data is available, how well organized the data is, and so on. I would caution, if you're going to do a student project, don't choose a model, a study with too much data or too many wells. If you have a basin that's very well known, take a small part of that basin, for example. Because if you say, my first study is going to have 40 wells in it and 20 pseudo wells, that's too many for an initial study. Make your first study one with 4 or 5, so that you get the feel of it. And that will be manageable in time, and you will figure out how long it takes you. I can tell you, building your first model is going to take you 10 or 20 times as long as building your 100th model. So it's highly variable, and it's going to vary from person to person also. You just have to work it out, but don't try too much the first time.
So the main tip is keep it simple, right? And the fewer the input, the fewer the errors on the modeling.
I'm sorry, I couldn't understand that. There's a distortion of your voice.
Oops.
Did you ask something about filtering?
Can you hear me now, Douglas?
Hello? 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 Hello?
Hey, can you hear me now,
Oh,
Douglas?
there you are. Yeah, I could see you again, and now I can hear you. Yes.
Sorry, I had some
I
problems
answered
with the
your
microphone.
question, but I don't. I answered your question, but I don't know if you heard it all.
Yeah, I heard it clearly, and I replied to you.
Okay.
So the main tip that you gave the students is to keep it simple, right? The fewer the, can you hear me?
Keep it simple at the beginning. Yes, really,
The fewer the input, the fewer the
don't bake a
errors.
wedding cake for your first cake.
Mm-hmm.
Yes.
The fewer the inputs, the fewer the errors, right?
Well, it isn't that all. I mean, that's part of it, but you can. It's just too much work. You're going to find as you get better, you can take shortcuts. You know where to look for data. You know quickly on a report whether it's going to have the data you want or not. You don't go through 800 pages one by one. You focus on where to find it within the report. Um, there's just a lot of ways in which you're going to find quicker ways to do things. Also, when you build your first model in an area, you could take that model and use it as a template for your second model. And then you can take one of your first 2 models, whichever one is geologically better for you, and use it as the template for your third model. That will make it a lot quicker to build multiple models. So that's a trick that you learn with some experience.
Perfect, Douglas. So I guess this was it. I don't know, do you have any final recommendations or considerations?
I'm sorry, I couldn't understand that. I think you said this is it, and then I lost it.
I don't know. Can you hear me now, Douglas?
Sometimes I hear some words and not others. Hello? Hello? Is anyone there? Is this the end? Okay. Well, thank you. Good night.